Hello. Well, it's telling me that I'm live. So let's assume that's correct. Hello, everyone. It's 4 o'clock. It's Thursday, and welcome to Earth Live. I'm Paul. I work for the Shark Trust. Welcome to my kitchen. I thought I'd try out something a little bit different today and talk to you a little bit about sharks. So firstly, thanks to Lizzie for inviting me to take part in this. It's really exciting. I hope there are lots of people listening and you're going to send me lots of questions. I'll try to answer them as we go, but I'll probably just get on a roll because I haven't got much time. I also want to thank all the other people that have been doing this. It's been really interesting kind of watching what everyone else is doing, and I've learned something along the way. I hope you all have too. So I have to start with a little bit about myself. So I'm a marine biologist. I have been a marine biologist for about 20 years. I actually discovered marine biology when I used to work in a very different type of job. I used to go home at night and watch television, watch David Attenborough documentaries. And my first love was actually through a program called Incredible Suckers. I think it's on YouTube. I advise everyone to watch it. It's amazing. It's all about octopus and squid. And I absolutely became fascinated with octopus, squid and cuttlefish. And that kind of drew me into becoming a marine biologist, went to university, and I've been working in it ever since. So I spent quite a lot of time working in public aquariums, working with the public, working with loads of different animals. And during that time, I really became fascinated with sharks. There's one here. Not only with sharks, but also with our reaction to sharks, how we respond to sharks, what we think about sharks, what we know about sharks, what we don't know about sharks. And that's really kind of become an obsession. And so for the last 5 years, I've been lucky enough to work for the Shark Trust. Now, the Shark Trust, if you don't know about us, check us out online, sharktrust.org. Not allowed to do that yet. We're a charity that is based in the UK, but we work all over the world, trying to create positive change really for sharks. So we do everything from kind of policy work, trying to persuade governments and policymakers to make better policies to protect sharks where they need protecting, or to manage fisheries. We do a lot of work with the industry, like the fishing industry, but also with diving industry, with ecotourism, with aquariums. So everywhere really where sharks and people meet, we try and make that a better relationship and a more positive one for both the humans and the sharks. So I think I'm the third person to talk about sharks in this series. So we had Gillian from Bimini talking about shark tagging and the work that they do over there in Bimini. And we had David Schiffman from Washington, DC, giving you a bit of an introduction to his work and some of the stuff that he knows about sharks. And I think for me, I wanted to talk about sharks, but I don't want to just kind of talk to you about sharks. And I haven't got any pictures, I've just got a couple of puppets. I really wanted to talk to you about shark science. I really want to kind of go into some of the science, because I meet loads of young people who want to become shark scientists, want to work with sharks, or want to become marine biologists. And they're always asking kind of what it involves and what can they do now to become shark scientists. So I think the first thing is, and I always kind of think that the first thing if you want to become a shark scientist, the first thing is you've got to become a scientist. You've got to start thinking like a scientist. And in school, we have a tendency, when we're at school, we have a tendency to kind of put science in different boxes. We have geography, and we have chemistry, and we have biology, and we have physics. And we kind of put these things in separate boxes. And sometimes it seems a bit difficult to work out how these all relate to what we might want to do in the future. So today I want to talk about a particular animal, one particular shark, and look at some of the science, delve into the science that's helped us to better understand these sharks and therefore to better protect them. Because I think the thing is, everyone knows a load of shark facts. I think if you were all sitting in front of me now and I asked, does anyone know a shark fact? Generally, I've got loads of hands going up in the air, and people get bombarded by facts. And there are loads of great shark facts around. I've got some here on my fridge. Thrown away all the pictures of the kids and got shark facts on the fridge. So a shark's bite is 14 times as powerful as a human's. Sharks have been around for 400 million years. Sharks have a sixth sense. Great facts. Greenland sharks live for 400 years. So these facts are great, and they're really cool, and they make the kind of shark seem more exciting and interesting. But did you ever find yourself thinking, how do they know? How do they know this? How do they know sharks have been around for 400 million years? Has someone been around watching? How do they know they've got a sixth sense? Has anyone asked the sharks how they sense their environment? Who's measured a shark's bite and compared it to a human's? How do they know? And the truth of the matter is that basically behind most good facts, there's some good science. And there's a whole lot of science that's gone in to produce this one fact that we just throw around from time to time. So I wanted to look at this one particular fact. I hope this is not backwards. If it is, well, read it backwards. Greenland shark lives for 400 years. This is a fact that's been around for a few years. People always throw it at me when I ask people about Greenland sharks. And so I wanted to kind of look at that and how we know that and the science behind that. So the Greenland shark, I haven't got any pictures. There's one on the advert for this piece. It's an animal that's steeped in legend. The Inuit had stories of Greenland sharks in their legend. They've been around for a long time, but they're also still steeped in mystery. There's still a lot that we don't know about Greenland sharks. We know where they live. They live in cold, deep, dark water in the polar regions. We know that we know what they eat. They eat because we can cut them open, and when we find them dead, and we can see what they've been eating. And they eat a lot of different stuff. The stomach contents analysis of Greenland sharks is fascinating. There's all sorts from fish, squid, to dogs and horses and moose and polar bears and seals. They are really, really varied eaters. So we know that. We know that they grow quite big. They grow to about 6 meters long. So they're the second largest of the meat-eating sharks behind the great whites. And we think that they live a long time, or we thought that they lived a long time. But we didn't really know until a few years ago exactly how long they live. And why is that? So how do we age a shark? Well, how do you age a shark? We know that sharks have got quite flexible skeletons, but David, if you're watching David Schiffman thing, he talked about the difference between bone and cartilage, and that shark skeletons are made up of cartilage. So they do have very flexible skeletons. But some of their bones, a few of their bones, do actually harden, they ossify. And when they do that, they create little rings, little annual rings, just like the rings in a tree. So for most shark species, you can age them by getting that bone, cutting it, analysing it under a microscope, and you can see how many years that shark's lived and worked out. And then you can look at sharks of different sizes, work out different ages, and look at their growth rate. So unfortunately for Greenland shark, it doesn't work, because Greenland sharks are what we call soft sharks. So their bones don't ossify, they don't go hard. So they don't have these growth rings. So really, up until about 5 years ago, all we really had was kind of educated guesses as to how long a Greenland shark lived. But then a team of scientists did what all good scientists do, and they said, we need to know the truth here. We need to know why, we need to know how we can age a Greenland sharks and find out a better approximation of how long these animals live. And the way they did this, I think, is absolutely fascinating. I hope you agree. I'm going to have to delve into the amazing world of carbon. And so we're going to kind of have to open up the chemistry box a little bit. Now, I am no chemistry teacher, so forgive me if I struggle with this a little bit. And I have my notes just in case. But I want to go through a bit of basic chemistry. So this is a piece of bread. So just like this piece of bread has basic ingredients, we know this bread has flour, has water, has yeast, has maybe a bit of sugar to make the yeast activate. We know that this piece of bread, although it looks like a piece of bread, it's made up of basic ingredients. And everything that we see around us, everything that we see, smell, touch, is made up of basic ingredients, and they're called the elements. Here they are, set out on the periodic table of the elements. Now, anyone who's at secondary school will be pretty familiar with the periodic table of the elements. It sets out all the elements in number order from left to right and down the page, from number 1, hydrogen, all the way to number 118, whose name I've written down here because I can never remember it, organesson, 118. It's a human-made element, like it's the 118th, and it's the last one on the periodic table. So everything that we know is made up of different combinations of these basic ingredients, just like a cake. And they all have atomic numbers. And the atomic number is basically dictated by how many of these small particles called protons, positively charged, tiny particles that they have in the atoms of the element. So for this, I've got a very handy chessboard here. I've got some drafts pieces. So the atomic number defines the type of element that you've got. And it also defines really their behavior. So if you have one proton, then you have, shout it out, I can hear you shouting, that's right, hydrogen. If you have two, then you have helium. If you were to have 8 protons, 2, 4, 6, 8 protons in the center, then you would have an oxygen atom. So the number of protons in the nucleus determines their atomic number, determines where they sit on the periodic table, and it determines a lot about the character of the element and how it reacts to other elements. And if we go to element number 6, number 6 is probably the most important element in all life. It's carbon. Now, carbon is a building block of everything that lives. It's all around us. Carbon is in my snack. Excuse me, I just need a little bit of water because we all have to drink water regularly. If you've got water with you, drink it now. A little sip, thank you very much. What was I saying? Carbon is in this orange. It's in my head. It's in every cell in my body. It's in this pencil. It's in this plum. It's in all the plants that are over there in my kitchen. It's in everything that lives. So it's a vital, vital element, and it's the building block of everything. But the interesting thing about carbon is that not all carbon is the same. And that is because we have these things called isotopes. These other particles that you find in the center of the element called neutrons. So we said we've got protons. These all have an atomic weight of 1. Each of these have weight of 1 and a charge of positive 1. Neutrons, no charge, so they don't affect how they react, but they do affect the weight. So each neutron also has a mass of 1. So by adding neutrons, you add the atomic mass. So you've got each atom has effectively two numbers. It's got a number and it's got a mass. And most carbon is what we call carbon-12. It's got 6 of each, 6 protons, 6 neutrons, carbon-12. However, sometimes, either through natural causes or through human-made causes, you can get more neutrons in the nucleus of an atom. So you might have 13, and this is called carbon-13. So basic carbon, carbon-12, you've got an extra neutron, you've got carbon-13, another one, you've got carbon-14. Actually, there are 15 known isotopes, each of these isotopes with different numbers of neutrons. And in the center, most of those isotopes basically in milliseconds just break down and turn into something else. There's no stability whatsoever. Carbon-12 is the most stable. It will never change. It will just stay like that forever and ever and ever for millions and millions of years. Carbon-14 is an interesting one because it decays but relatively slowly. So it's got what we call a half-life of 5,739 years. Very predictable. In 5,739 years, there'll be half as much carbon-14 as there was, and another 5,739 years, there'll be another half again, and it will go down and down and down and down like that. So having these two things together, carbon-12 and carbon-14, existing in nature together, it's quite interesting because one's stable and one isn't. Now, carbon-14 is being formed all the time. It's actually formed from nitrogen, which is going to be bombarded by the sun's rays in the upper atmosphere, and then as it's created and carbon-14 appears in the atmosphere, it gets integrated into carbon dioxide, which is present in the atmosphere, alongside carbon-12. Always in this same ratio, always in this kind of, it's basically 99% carbon-12, almost 1% of carbon-13, and then a tiny, like a trillionth of carbon-14. And then if it's in carbon dioxide, then plants will take it up when they respirate, and they will then integrate it into the plant's fibers, into the trunks of trees, into the leaves and so on. And then the animals will eat the plants and the carbon will go into them, and then other animals will eat the plant-eating animals and it will go into them. And every bit of carbon that's integrated into all life has this signature. And just to kind of demonstrate that, if you think about, I mean, this is wildly out of proportion, slowly, more formed, more decaying. So over millions of years, the amount has stayed stable. And that stability, that ratio between the two, and that knowledge of how carbon-14 and carbon-12 behave is the basis of carbon dating. It's how we're able to kind of tell how a bone is when a scientist finds it, or how old an artifact is when we dig it up and an archaeologist digs it up. And that's carbon-14 dating. It's great for things that are really old, but it's not so good for things that are relatively young. And so it's not that great for telling us, about giving us any clues as to how long Greenland shark has lived. But something happened about 70 years ago, which gave us a new tool in this investigation. I'm just checking my time. I'm going to run over. So something happened, and that was nuclear testing in the 50s and 60s, sorry, 40s and 50s and early 60s. All the nations were doing lots of nuclear testing. When you nuclear test, you create lots more carbon-14. So suddenly, there's a lot more carbon-14 going into the atmosphere, and it creates a spike. And then gradually over time, it drains back. It's decaying away. Over the last 17 years, it's been decaying away and away and away and away until eventually it will return to the background level, which it's been for millions and millions of years. But this spike is quite predictable. So it's basically something that's locked in everything that's been born in the last 17 years, because bizarrely, we have a little crystal in our eyes, a little lens crystal. Excuse me, that's one of the kids shutting doors upstairs. We have a little lens crystal in our eyes, which is formed when we're born, and it doesn't change. So it locks in that ratio of carbon-12, carbon-14 that was relevant when we were born. So by looking at that eye crystal, we can tell how much carbon-12 to carbon-14. And like on a graph, if there was this much in, say, 1960, this much in 1970, this much in 1980, this much in 1990, and so on, you've got that predictable relationship between the ratio and year, then you can quite easily age something that was born in the last 70 years to quite a degree of accuracy. And this is what the scientists used to help them find out that the Greenland shark was 400 years old. How? Well, very basically, they took 28 samples of Greenland sharks from fish markets or from scientific expeditions, all from little tiny ones through to the biggest one they could find. And they analysed the eyes of all of those Greenland sharks. And for all of the ones that were smaller and younger than 70 years, they're able to put a really accurate age, and then they're able to graph their age against their size, and then they can work out a growth rate, and then based upon that growth rate, they're then able to extrapolate that back to all the really big ones, and they found the biggest one, they estimated that the biggest one had lived around about 400 years. Actually, they estimate somewhere between 272 and 512 years, because there's a lot of error as the graph goes backwards, but essentially 400 years. That great long explanation is how they find out that fact. And for me, the great long explanation and learning all about carbon-14 and how carbon-14 works and how we can use it for dating things, and how we've used it kind of since this really strange and pretty awful thing of nuclear testing, how we've been able to use that to find out this amazing fact. That's more interesting than the fact itself. So for me, my message here today is, if you want to be a scientist, always when you hear a fact, ask, how did they do that? How did they do that? And dig into it. And if you really want to be a scientist, if you're not happy with how they found it, or you're not happy with their result, then go further and see if you can disprove it and come up with a better answer. So science, for me, when we're at school, it's in all these little boxes. But when you get into the real world, and when we're doing something applied, like working with sharks, we're mixing up chemistry, biology, geography, maths. We're using mathematic modeling to work out the age of these Greenland sharks. We're mixing up all these subjects again, and that's when it gets really interesting. And that's when all the work that you do at school suddenly becomes worthwhile. Now, I have had my 20 minutes. There are a few questions on here. I haven't got my glasses on, so I can't actually read enough. While I'm quickly reading those and seeing if I can pick out a couple of questions, if you want to know more, about the Shark Trust, if you want to know more about sharks, check out sharktrust.org. There's a pups club on there. There's games and activities for all ages from kind of 7 up to 70. Follow us on Facebook, follow us on Twitter, find out more about us, become a member, support us in one way or another, because sharks are awesome. There's so much more to sharks than we know, and there's so much more to find out. So I'm just going to pick one question. Wow. Do we know how many Greenland sharks are on the planet? Which is from Phil, age 10. No, basically. That's a really interesting point. Sharks, I mean, one of the amazing things about sharks is how little we know about them. They're these huge animals, and yet we know so little about many of them. And certainly in terms of numbers, a lot of what we do is kind of educated guessing or modelling. And so, I don't know, there may be a scientist somewhere who could answer that question, but I'm not one of them. So no, I don't think we do know how many Greenland sharks are on the planet or in the sea. James Redcliffe has asked, I'm going to take this as the last one because I know Lizzie probably wants me to stop. Is the Greenland shark threatened by climate change? That's a really interesting question. Are sharks generally threatened by climate change? And the answer is probably, actually, if you go back through the series of Earth Lives, there's a good one by David Schiffman who talks about climate change and plastics and other threats to sharks. And really, we always say, as he said, that the biggest threat to sharks is overfishing. If you take the Greenland shark as an example, what we did find out through this aging thing is also when they reach sexual maturity. So they don't reach sexual maturity until 156 years old. So that means that if we were fishing sharks in the early part of the 19th century, and we fished sharks to a degree where their populations were depleted, they still wouldn't have recovered for another 20, 30 years because it takes them that long just to reach sexual maturity. So overfishing is the big threat. Climate change will have an impact. It's impacting on everything in the sea. In terms of sharks, potentially it might mean that their prey move, because some of the smaller prey, certainly things like basking shark, which feed on plankton, and the plankton will shift their range very, very rapidly in response to climate change, might mean they have to change their range. We think that ocean acidification is possibly having a detrimental effect on some sharks and on their dermal denticles, the teeth on their skin. And we also know that some sharks are affected by plastics pollution, but we still say that overfishing is the big one, and that is something that we can deal with. It's relatively easy to deal with. We just need to move towards sustainable fishing and sustainable fishing methods. So I'm going to go now. I'll stick around for a bit and maybe answer some of the questions on the live chat. As I said, thank you very much for joining us. Thank you very much for Lizzie for running these Earth Live events. And please check us out on sharktrust.org and find out more about sharks and learn to love sharks as much as I do. Thank you. Bye.